This is lecture 28, and I'm going to introduce you to the Poisson process. Okay, so remember last time we talked about the continuous time Markov chain? So basically, a continuous time Markov chain is similar to the discrete time Markov chain in that it satisfies this Markov property here, and that you have this probability of being in chain S, being in state J, 2 units from now is given by this Pij, which depends upon your time and how much time has elapsed. And so now we're talking about having discrete time instead of continuous time instead of discrete time intervals. Okay, so a Poisson process is a type of continuous time Markov chain in which your time is considered to go from 0 to infinity. Your state space is just your 0, 1, 2, etc. So a subset of our integers. Okay, so the following two properties define the Poisson process. So first of all, at t equals 0, we assume that x of 0 is equal to 0. And we're going to talk about why these are in just a little bit. And then we also assume that we have these certain transition probabilities. And so I'm not going to go into great detail here because I want to give you an intuitive idea before I actually go through what each of these means. But basically, this is your probability of transitioning from state I to state I plus 1, so just adding 1 to your state I. This is the probability of staying in the same state, and this is the probability of transitioning to some other state, and that state is actually greater than or equal to I plus 2. And here lambda is the rate of the process that we're talking about. So again, this is one definition for a Poisson process. There are more definitions. We're not going to spend a lot of time on the Poisson process because I want to get to how people use continuous time Markov chains for modeling purposes. But the Poisson process is one in which I think it's important enough that we need to go ahead and examine it. But first of all, what I want to do is I'll go through an intuitive idea of what the Poisson process is, and then come back to these probabilities in just a few slides. Okay, so the Poisson process is better known as a counting process. So think about this as a way to count how many arrivals arrive. So you can think about how many people are coming in if you're in a hospital. How many people are you getting in a certain time interval? So normally the time interval here represents time. So we have a stream of events. So we assume that we're starting at t equals 0 whenever our beginning time that we're going to start counting. We assume that is t equals 0. And then n sub t is the number of arrivals which occur between our starting time 0 and whatever time we're talking about, time t. So what we have, for instance, n of t may represent the number of text messages you receive at a certain time. And again, I talk about people entering a building, how many calls you might get in a certain time period, emails, so obviously you can see any kind of counting process. You can think about maybe being a Poisson process. So here, in a Poisson process is just a special type of counting process. So n sub t, for the way that we've described it here, is the number of arrivals which occur by time t, is a random variable. So these collection of random variables is an integer value stochastic process. So we have integer values 0, 1, 2, etc. How many have arrived? We assume we can't get half of an arrival, right? So as t increases, the number of events has to increase. So if you have some time smaller than what the time you're looking at now, so if s is smaller than t, then the number of arrivals at time s has to be less than or equal to the number of arrivals at time t. So you're assuming it can only go up. You've already counted them. You're not assuming that they're leaving. You're only counting the number of arrivals. Okay, so now if we go back to the definition of Poisson process, it might make a little bit more sense. And so the first property was that t equals 0, x of 0 had to equal 0, which makes sense if this is a counting process because at initial time we're assuming that there have been no arrivals. So it makes sense that you have to start out x of 0 has to be 0. You're assuming you start at time t equals 0 and that you have no arrivals to begin with. Okay, so now back to the probabilities that we had. So here we have the probability of transitioning from state I to state I plus 1. So now if we think about what this is, so this is the probability that in time delta t, the way that you can think about this is if I had counted I arrivals in my one time slot, then I now have I plus 1 arrivals in this time span of delta t. So basically what this means is this is the probability of a single arrival in the period. And here, whenever you see delta t, you're going to see delta t a lot with continuous time Markov chains. Delta t, you're assuming, is going to be a small interval of time, just like in Calc 1 when you talk about delta t. So delta t, you're assuming, is going to be some small interval of time, and only one event can really happen during that time interval. So it's the same idea here. So here we're thinking that the event is an arrival because we're talking about a counting process. And so in this time period delta t, this is the probability that you have a single arrival. And this was what we were given before, but this makes sense because here if lambda is our rate, then you have the rate of arrival times the time interval. In this order of delta t, what this means is if you have something of order delta t, basically if you take the limit as delta t goes to 0, if you have f of delta t or of delta t, then this set goes to 0. So that's what it means to be order of delta t. So if you take this function that's of order delta t divided by delta t, and take the limit as delta t goes to 0, you basically get 0. And we're going to see where this comes into play a little bit later. Okay, so again, here this was possibility of going from state I to state I. So if we think about how to write this slightly differently, this is the probability that we have no arrivals during the time interval delta t. And this was given as 1 minus lambda delta t. And think about what this means. And so on the previous slide, we had the probability of increasing by 1 arrival was lambda delta t. The probability of staying at the same count, think about staying at the same count, is 1 minus lambda delta t. So if you remember probabilities, you have a probability and they have 1 minus that probability. So basically what we're saying is that in this small time delta t, you can only do two things. You can either stay the same count or you can increase by 1 count. And the probability of I going from j, if you're bigger than just that 1 count, what this means is it's basically negligible. When you see something as order delta t, it means it's negligible. There is the possibility that that would happen, but it's so small that it's not really worth considering, is the way you can think about that. Okay, so here we have independence. The p, j, i of delta t are independent of I and j, and it only depends upon delta t. If you have two non-overlapping intervals, and you look at x of t plus delta t minus x of t, and you have the interval, the s plus delta t and s, or s and s plus delta t, and you look at these two non-overlapping intervals, they both differ by delta t. They're both independent, but they have the same distributions. So these are two totally different intervals, but they have the same distributions because you're only looking at what happens in a time frame of delta t. So here I've gone from s to s plus delta t. My interval here is a length of delta t. The interval here is a length of delta t. So what we have is that these processes are independent, but they do have the same distribution, so they're going to behave in the same way. So basically what we have is a Poisson process has stationary and independent increments. Okay, so more of the description about it is the Poisson process is defined as a process with stationary independent increments, which we already said, for a fixed t. And x of t has a Poisson distribution with parameter lambda t. So this is actually what we're going to derive. So we're going to show that the Poisson process, if you have a random variable that behaves according to a Poisson process, or if you're assuming you're modeling using a Poisson process, then what you're going to get is a Poisson distribution with parameter lambda times t, where here lambda is your rate and t is the time increment you're talking about. Okay, so we're going to show that this has, that a Poisson process does have a Poisson distribution. So recall from lecture 10, which has been many lectures ago, I know. So the Poisson distribution is given by this function. So basically what we want to show is we want to show that the probability that x of t is equal to some state I, which we're going to define as pi of t, is given by, so we're assuming we want to show that it has a parameter lambda t, right? It has a Poisson distribution with parameter lambda t. So everywhere we see lambda here, we really want to have a lambda t, because we're assuming that is our parameter that we have our Poisson distribution. And so here we have lambda t to the I, e to the minus lambda t over I factorial. This is what we want to show. We want to show the probability that x of t is equal to I is given by this. Okay, so let's start off by defining the probability that x of t is equal to I. Then how do we actually get there? How do we get to the state I? So there's two ways of getting to state I. If you look at this first part, the first way of getting to state I is if I was in state I and I stayed in state I. So the probability that my x is equal to I, so I'm in state I, the probability that I'm in state I at time t plus delta t is equal to the probability that I was there and stayed there. So remember, staying there had this probability of 1 minus lambda delta t, plus the probability that I was in one state less and I moved there. So here's the probability that I was in one state less. This is the probability that I moved there. Remember, lambda delta t was that probability we looked at before. Similarly, we can define P0 of t plus delta t. So this is our initial. Remember, this is probability that x of t is in state 0. Remember, that's where we started, right? So the only way that we can still be in that state at time t plus delta t is if we stayed in that state, if we didn't move up, because we can't move back down. So here's our P0. So again, this is just what I said. Poisson process starts there, so the only way to get there is if there were no arrivals during that time period. Okay, so now what we can do is we can write this. So here we take our P sub I of t plus delta t, which we just defined on the previous one, minus P sub I over delta t. So this kind of looks like Calc 1 where you were looking at derivatives. So this is exactly what I had written down before. So my Pi of t plus delta t was given by this first part. I'm going to subtract off Pi of t and divide it by delta t. So if I just simplify a little bit, my Pi's cancel. Pi of t cancels. I divide through by my delta t, and my delta t and my first two terms cancel out. And so now I can take the limit as delta t goes to 0. On the left-hand side, we get our derivative. And on the right-hand side, remember what happens. Limit as delta t goes to 0. This part goes to 0. So we have dpi of t over dt is equal to this. Why do we care? Well, what we're trying to do is we're trying to derive a formula for pi of t. We're trying to show that it satisfies the Poisson distribution. So what we have is that if we have some initial time, hopefully we can find what our next time step should look, what our probability of pi should look like. So let's do this for P0. So P0 would give us our initial, our being in state 0. So P0, if we have P0, then we could find P1. If we have P1, we could find P2. That's what this says. So I could solve this differential equation if I just had the previous one. Okay, so let's find P0 because that's where we would start off with. So P0, do the exact same thing. We write down this part, we simplify and get rid of P0 of t. We divide through by the delta t, and then we take the limit. So when we take the limit, this part goes away, and we're just left with this part. Okay, well this is something we can solve. So anybody who's had differential equations, which most all of you who have had differential equations, can solve this. So to solve this, basically you can separate variables. So I divide by the P0 and I move the dt to the other side. So I integrate. When I integrate on the left, I get natural log. On the right, I get minus lambda t. I have my plus constant. So I multiply both, I raise both sides to the exponential. So I get P of t is ae to the negative lambda t. Use what we know about initial conditions. So P0 of t is the probability that x of 0 is equal to 0. Well, that's 1 because x of 0 can't be anything but 0. That's the property of our Poisson process. It has to start in state 0. So P0 of t has to equal 0. That means that A has to be 1. So we have what P0 of t equals. Recall, we want this to look like our Poisson distribution. Our Poisson distribution says that we want to have Pi of t is equal to this. Well, P0 of t would then be this part, which is exactly what we got. So we're well on our way. If we have P0 of t, we can use it to solve P1. This was our differential equation, so Pi, where I is 1 now. So we substitute in what our P0 that we just found. We can rewrite this by moving the P1 on one side. So you don't have to know how to do this, but so just from differential equations, the way that you would solve this is by using an integrating factor. So my integrating factor here would be e to the lambda t. Multiplying both sides by an integrating factor, basically what we have is this left-hand side is a derivative. And it's the derivative of e to the lambda t p1 of t. Right-hand side just gives me lambda. So if I integrate, if I separate and then I integrate, I'm going to have the integral of this is just going to give me e to what's inside, the e to the lambda t p1. And integrate this, I'm going to have lambda t, and I'm going to actually have a plus c here. So then here I have what p1 of t looks like. And I believe if you actually work it out, c ends up being 0 on each of these. So if I use P1 then to find P2, I get this formula, and then P2 to find P3, etc., etc. So what that actually gave us was exactly what we wanted in showing that the Poisson process has a Poisson distribution. Okay, so next time we're going to do a summary of the exponential distribution and the Poisson process, and then we're going to do some examples.